Absolute and apparent magnitudes. This third video on astrophysics shows how we can classify stars by their visual brightness, and astronomers do this using the magnitude scale. As always on this channel, you can expect a clear and concise explanation of each topic. Please don't forget to click on the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. Astronomers prefer to talk about a star's brightness as seen from Earth rather than its luminosity. The brightness of stars is usually given in the magnitude scale. Astronomers measure star brightness in units called magnitudes, which seem at first counterintuitive and confusing. That's because they are counterintuitive and confusing. They are in large part a legacy of ancient times. But you may wonder, if this system is confusing, why do we still use it? Well, it may be confusing, but it is convenient. The stars you see have a wide range of brightness. The brightest star visible with the naked eye is over 600 times brighter than the faintest one. So astronomers are dealing with large numbers, and the magnitude system is logarithmic. Logarithms are a convenient way to express large numbers. Let's start with a brief history of the astronomical magnitude scale. Hipparchus was a Greek astronomer who lived about 2,200 years ago. He was the first person to classify stars by brightness. Hipparchus called the brightest stars first magnitude stars. Then he listed stars as second magnitude and so on down to sixth magnitude stars, which were the dullest that could be seen by eye. Of course, he did not have binoculars. The apparent magnitude m of a star in the sky is a measure of its brightness as seen from Earth, which depends on the intensity of the light received from the star. During the 19th century, astronomers attempted to make the scale more precise by establishing exactly how much the apparent brightness of a sixth magnitude star differs from that of a first magnitude star. Measurements showed that we receive about 100 times more light from a first magnitude star than from a sixth magnitude star. Therefore, the main rule of the magnitude system is that a difference of 5 magnitudes corresponds to a factor of 100 times in brightness. If two stars have magnitude values that differ by 5, the star with the lower magnitude is 100 times brighter. It is important to understand that the lower the apparent magnitude value, the brighter the star. Conversely, the greater the magnitude, the dimmer the star appears. So a first magnitude star is 100 times brighter than a sixth magnitude star. Or conversely, a sixth magnitude star is 100 times dimmer than a first magnitude star. But what if two stars differ by 1 magnitude? In short, if two stars differ by 1 magnitude, how many times is one brighter than the other? Let's think a little. If a first magnitude star is 100 times brighter than a sixth magnitude star, so we need a number that when multiplied by itself 5 times gives this factor of 100. The answer turns out to be about 2.51, which is the fifth root of 100. This means that a magnitude 1 star is a magnitude 2 star differ in brightness by a factor of 2.51. The difference is 2.51 times for each step of magnitude. In short, Each order of magnitude is 2.51 times brighter than the previous one. So a magnitude 1 star is 2.51 times brighter than a magnitude 2 star, and 2.51 squared than a star with an apparent magnitude of 3, and 2.51 to the power of 3 than a star with an apparent magnitude of 4, and so on. We can generalize this formula. Consider two x and y stars of apparent magnitudes mx and my, whose apparent brightness are bx and by. Every difference of 5 magnitudes corresponds to 100 times more light intensity from x than from y. This equation tells us how to convert from a magnitude difference to a ratio of brightnesses. To go in the other direction, we take the logarithms, base 10, of both sides. We use the power rule, and we rewrite the equation. Swapping the right and left-hand sides of the equation, we obtain. If you take the inverse of the fraction, the logarithm becomes negative. Thus, the minus sign ensures that magnitudes are a measure of faintness. If by y is less than bx, star y is fainter than star x, then the brightness ratio is less than 1, and the log of the ratio is negative. So m2 minus m1 is positive, and the fainter star has the larger magnitude, as expected. The magnitude scale expresses a given ratio of brightness between two stars as a difference in their magnitudes. Mathematically, the brightness bx and by of two stars with corresponding magnitudes mx and my are given by the following equations. Modern astronomers use a similar scale for apparent magnitude. With the help of telescopes, the scale extends beyond 6 for dull stars and below 1 for very bright stars or planets. The larger magnitude on negative scale, the higher star brightness, while the larger positive magnitude, the fainter the star appears. Let's see how this works by solving two problems involving apparent brightness and apparent magnitude. The apparent magnitude of the Sun is minus 26.8 and the apparent magnitude of the full moon is minus 12.6. By what factor is the Sun brighter than the moon? We can use the first equation above. The Sun is about 480,000 times brighter than the full moon. Consider Sirius with apparent magnitude minus 1.46 and Spica with apparent magnitude plus 0.91. By what factor is Sirius brighter than Spica? Sirius is about 9 times brighter than Spica. Apparent magnitude is a measure of the apparent brightness of a star as seen from Earth. So apparent magnitude describes how the stars appear to be. However, they tell us nothing about a star's true brightness because a star's apparent brightness depends on the star's true brightness and also the distance to the star. Therefore, two stars of the same apparent magnitude may not be equally brightness, as they may be located at different distances from the Earth. Now, we could easily compare the true brightness of stars if we could place all the stars at a fixed distance from Earth. Differing distance would not then be a factor in how bright the stars appeared. Instead, the differences in magnitude would be due only to differences in luminosity, and as such these values would be absolute. With this idea, astronomers define the absolute magnitude of a star as follows. The absolute magnitude m of an astronomical object is defined as its apparent magnitude if it were at a distance of 10 parsecs from the Earth. Let us now relate the absolute magnitude of a star to its apparent magnitude. Consider a star with apparent magnitude lowercase m and brightness received at Earth, a distance d from the star b. Now, when the same star is placed at a distance of 10 parsecs from the Earth, then its magnitude would be capital M and brightness received at Earth from the star b10. Then we use the formula above. The luminosity of a star is a measure of the actual brightness of a star, and the apparent brightness of the star is related to its luminosity L as follows. We can rewrite the formula. We can use the properties of logarithms to finally obtain the difference between the apparent magnitude and the absolute magnitude is called the distance modulus, since it is directly related to the star's distance d from the Earth. The above equation shows that if a star's distance is known and its apparent magnitude is measured, then we can determine its absolute magnitude. Conversely, if we know the absolute magnitude of a star and its apparent magnitude, we can determine the distance. Rearranging the above equation gives We now summarize the equations. Let's see how this works by solving some problems involve absolute magnitude and distance. Calculate the absolute magnitude of the following stars. If we know the distance to a star in parsecs and its apparent magnitude, we can calculate the absolute magnitude using the formula we have just deduced. This example illustrates how apparent magnitude is often a poor indicator of how truly bright a star is. Although Procyon and Betelgeuse appear almost identical to the eye, the two stars have radically different luminosities. Betelgeuse is the more luminous of the two, but to the naked eye it appears to shine less because it is much further away from us than Procyon. Calculating the absolute magnitude of the Sun, we can see that if the Sun were 10 parsecs away from us, it would hardly be visible to the naked eye. Cepheid variable stars. Cepheid variable stars have a remarkable property. They have a periodic variation in luminosity that has a constant known relationship with their maximum luminosity. From measuring the period of their variation in luminosity, their absolute magnitude can be calculated, thus yielding accurate estimates of the star's distance using distance modulus equation. Astronomers can identify them not only in our galaxy, but in other nearby galaxies as well. If one requires the distance to a given galaxy, one first locates the Cepheid variables in this galaxy. Such stars have been used to determine distance to star clusters or galaxies well beyond what is possible from parallax measurements. Astronomical objects such as these, for which the luminosity can be calculated directly, are called standard candles. Let's see how this works. A Cepheid variable star is observed in another galaxy that is close to the Milky Way. From its period variation in luminosity, its absolute magnitude is determined as being minus 3.6. It is observed to have an apparent magnitude of 15.56. Estimate how far the galaxy is from Earth. We take the second formula to find the distance.